Okay, this is the model. It's with Revit. Apparently, everything is correct. We have false ceiling. We have spaces here up to the false ceiling or up to the roof here. Okay. If we open the plan, everything seems correct. Even if we open the Analyze tab with the heating and cooling loads, we have everything here. We go to details, and apparently there is no warning, so everything should be fine. Okay, but if we open the loads report, we have number one, number two. Yep, we open number one. So the numbers, it's 123 and 70. Number two, it was number two, 155. Okay, it works. So the second report should be better than the first one. But now we are going to analyze the second one, which is apparently is the best one. We are going to analyze this, and if we go to the detail, okay, here we have the building components, the wall, the window, the door, the roof. The first thing that we have to notice is through the walls we have 300 BTU hours, 350. Okay, that's fine. We are working with passive house standards, so that makes sense. What about the window? The window, it's 45 for cooling and 9 for heating. Does it make sense? Yeah, windows, if we have because we have selected a triple window, so triple windows, low emissivity coatings, those are good for winter. But in summer, if we don't have any shading device, or we have the sun just directly striking the window, we have an issue. And here we can see this is 9,000 in winter for heating, 45,000 in summer. So this is not acceptable. It doesn't make any sense. So we can reduce this load, and this is the design. So we are designing something very basic. It's just a box. So we don't have any shade here on those windows, and that is affecting the summer performance or the cooling performance. Okay, but we know that the design is not the best one. Okay, so it makes sense that windows in summer have a higher cooling load than the heating load in winter. Makes sense. What about the roof? The roof, it's 35,000 in cooling and 36 in heating. Again, does it make sense? Does it make sense that in the heating load is higher than the cooling load? It makes sense because we all know that the heat tends to go up. So in winter, if we have the same detail, it makes sense that we have more heating than cooling. We have a higher heating load. It's higher than the cooling load. Okay, so everything makes sense. But what it doesn't make any sense is that the heating load through the walls is 1,000, and the heating load through the windows is 36,000. Is it because the first thing I think is, okay, so there's a mistake here in the roof. It doesn't meet the passive house standards. So Zach has done something wrong, and I opened this, and I'm sure that this roof is not R80. No? Yes, it is R80. So sorry, Zach, you did well. So what can I do now? It's R80, and the heating loads through the roof are that high. Okay, let's see if there's something wrong here. So I'm going to select this, and this is what Nash did. So he selected the roof, roof. Okay, he selected the roof, edit type. We edit this type. We have R80, okay? And we have a rigid insulation, 1 foot and 1 inch. Okay, so let's make it double. So let's say 2 feet and 2 inches. We click OK. Now the thermal resistance is 157. Okay, so I think it's too high. 80 is enough. We have 157. We apply. Now the roof is much thicker. And let's calculate things again. So we analyze, calculate heating and cooling loads, calculate. And what is, so this is loads report 3, and this is the original one. Okay, so look at the first, it's what it, so the cooling load is 100,000. The heating load is 55,000. So here we have exactly the same, 55 and 100. Hmm? And what is the roof? It's 35 and 35. Yes, we have slightly reduced this, but it used to be 35 and 36 and now 1000, and now it's 35 and 35,800. Okay, so what's going on here? Can I keep on increasing the thermal insulation of the roof? Can I have R value 200, 300, 1000? No, there's something wrong here. Okay, so let's go over the loads report. Okay, and let's analyze. That's why it's important that we can analyze different spaces here. So we have the office 1, 2, 3, 4, and then we have the lobby. And okay, so something strange here. The lobby is the largest space, and all these huge windows are in the lobby. But if we analyze the load report, the lobby has the lowest heating load. Hmm? Why? If it's the largest space, it has the highest amount of windows. Why the hell is the highest heating load? Doesn't make sense. Okay, so let's find out what happens here. And then we go space by space. So this is office 1. So in office 1, we have the same pattern. We have the window, it's quite high in heating and cooling. It's always higher in cooling than heating, the windows. The roof, it's very high, but is higher in cooling than in, well, it's higher in cooling than in heating. This is not, well, I don't know why, but anyway, it's too high, okay? Even the windows here, it's 900, and the heating load for roofs is 8,000, almost 9,000. This is office 1. In office 2, we have the same pattern, 92. So this is 200, 900, and 8,000. This is 92, 100, 900, 8,000. Office 3, it's almost 100, 900, 8,000. Office 4, this is office 4, 200, 900, 8,000. Okay. What happens with the lobby? The lobby, 700 through the walls. Makes sense because we have the highest wall area. 6,000 through the windows. Yeah, we have a lot of windows in the lobby. 300 in the roof. Okay, in the rest of the spaces, it was 8,000. If we analyze the roof, the lobby roof, it's only 300. And again, we have the highest area. There's something wrong here. Okay, so is Revit doing something wrong? No, Revit doesn't make any mistakes. We make mistakes, and Revit says, okay, your wish is my command. You want me to calculate this? I do it. But for sure, we have made a mistake somewhere. So where it can be? Well, it's here. Okay, so you see that here we have the false ceiling. Zach did what I told him to do. If this is level 3, so this space, so I'm selecting the space here. So that space is can be up to level 3, and then it will be that way. I thought that was the mistake, okay, because maybe I have created that that space. The room boundary is the false ceiling, and this is something that I have found out. When Revit doesn't have a space, if you are creating spaces, so if you don't have a space here, Revit considers that this is outside. Now it makes sense because the roof of this office space, this roof is just this gypsum, just 1 inch false ceiling, which is made of gypsum. Well, I think it's 2 inches, that is the same. We don't have any thermal insulation here. So Revit considers that from this space, we are losing a lot of heat going up because this is outside. Why? Because we don't have any space here. So what Revit considers is that we don't have spaces, that is outdoors. So we have to fix this somehow. How can we fix this? Will it make a difference if I select all these and instead of going up to level 3, level 3 is where the false ceiling is, I make this up to level, what is that level? Level 2. Up to level 2. Okay, so now I select that space and this goes up to level 2. If I do the same, because I'm working with this section, let's work with section 2. On section 2, we have this, it's up to level 1 and the limit offset is 10. Let's make it up to level 2 and no offset. Okay, if we select this, now we see that we have the false ceiling, but the space boundary is here. It's at the, it doesn't happen, well, it doesn't happen in the lobby because in the lobby we don't have a false ceiling. So that explains that in the lobby, in this load report, if we are looking at the lobby, we don't have heat losses through the roof because in this case, we don't have a false ceiling and we have an R150 roof. Okay, so now in section 1 and in section 2, we have those spaces here. What about this one? Okay, I can change this in plan. So I can say that this is up to level 2. This is 0. I select this. This is up to level 2. And this is 0. So now all these levels are up to level 2. Does it make any difference? So let's calculate again. That makes me because the level doesn't get to the same level here. Okay, so it doesn't get to the roof level. So I don't know. Let's calculate this. We have load report number 4 and nothing has changed. Okay, so the roof is still 35,800. So I'm going to delete report number 4 because it didn't work. So how can I make it work? Okay, so if you select the false ceiling, here you see that this is the room bounding. Okay, so this is the boundary. If we do this, that means that either we create a space here, so we have to create another space here between the false ceiling and this slab. I can do that, or I can disable the room bounding, and now the level goes up to the roof. Okay, so I'm going to do this in section 1 and section 2. So here I don't select room bounding, and now the level goes up there. Let's calculate another heating and cooling loads. Okay, now I see that that makes sense. I have done this with these 2 office spaces. This is office 1, 2, 3. So 2, 3, the space goes up to the roof. In 1 and 4, the space goes up to the false ceiling. So let's calculate this and let's see if there's a difference. Okay, we have reduced this a lot. Now it's not 35, it's 18. And now if I go to Office 1, in Office 1, the roof is still too high. The heating and cooling load through the roof is still too high because I haven't changed the false ceiling in Office 1 and 4. What about Office 2? In Office 2, the roof, okay, it's 50 and 89. That makes sense. Okay. So what do I have to do now? I have to I have to select the false ceilings. I can do that. I can change the sections, this one and that one. And now in section 1, we select the false ceiling. We don't have a room bounding. I select section 2. I do not want the room bounding, and now it works well. Okay. So finally, I calculate heating and cooling loads. Now all levels are at the same, well, they have the same boundary, which is the roof itself. We calculate, and now, yes, it makes sense because we have reduced the heating loads a lot. And now through the roof, we have 700 in total. Okay, so we have 1,500 through the wall, 10,000 through the window, 700 through the roof. Okay, so it makes sense now. So there was a mistake, and there was a mistake that I hadn't noticed. If you didn't have a false ceiling and you just create that space, by default, you create that space from the floor to the roof. Okay, that's fine. If you create a false ceiling, you can do that. And you can do this in terms of design because you want to hide the equipment or the mechanical systems we have here. But then you have to make sure that this is not the roof boundary. And if it is the room boundary, we have to create another space here in the false ceiling, which is too much work. So I don't recommend you do that unless we have an attic space. So if we have an attic space, maybe it makes sense to create another level in a space that it doesn't have a heating or cooling. Okay. So that's why how we get to understand these kind of things. So can we trust Revit? No, don't do that. Trust your own criteria. Look at the report, and if you find something that doesn't make any sense, try to find out why. And in this load report number 3, having this heating load in roofs when we have an R value, the R value is 150, there should be something wrong here. Can we find out in a different way? Yes, we can. And I told you to use this ASHRAE. Okay, so comparing this, we can have an idea of what we do. So let's do this. If we select the roof, here we have the area. The area of the roof is 2,047, around 2,000. And the R value of the roof is 150. Okay, so if we try to do the same here with this Excel file, now the R value is 120. We can make it bigger by increasing the width of thermal insulation. Let's make it 40. No, it's too much. Let's make it 30. 33. Okay, so now it's 150. The R value is 150. The area of the roof, it was 2,040 something, 2,040. And what is the roof heating load? 800. What is the roof heating load in this report? 700. Okay, that's fine. Okay, so this is what we what we need to understand, if we are working with passive house standards, the weakest point should be the window. Especially is the window in summer, in cooling mode. If there is something else that if we have a high thermal load in walls with passive house standards, or a high thermal load in roofs with passive house standards, I think there should be something that we didn't do well, and it's not Revit. Revit understands that if you have this element as a room bounding, this is outside, period. Okay, but it's not. So we can do this, and now we solve that issue. We have a false ceiling. We can hide all the elements here, but that space is considered from the floor to the roof. Okay, so do not trust anything. Do not trust any software. If you have experience, you will get to know, okay, that's impossible. There's something wrong, and then you find out what's wrong. But if you don't have any experience, any number for you, it's fine. Okay, 5,000. Okay, it's fine. 50,000. Okay, why not? So try to compare different things, and by comparing different things, you get to know if things are right or wrong. Okay, and I have provided you with this. This is quite easy. This Excel file. We just have to place the thermal conductivity, the width, and the area of the floor or the roof or the wall, whatever. And here you have something that, and I don't mind if this is 1,800 and in Revit you have 1,500 or 2,000, that's fine. But if you have here 1,000 and in Revit you have 50,000, there's something wrong, either here or in Revit. Okay, so keep on working. We are working with this simple model. Imagine that if we have hundreds of spaces, 3, 4 floors, we have spaces that have a heating system, other spaces that don't have a heating system. It can get much more complicated. So first, we need to gain ability to do this by analyzing rectangles, and then we can move on to more complicated things. When we are sure, when we select spaces, we have a lot of information about the space. Okay, so we can change the number, and I recommend you change the number so that we understand what we are doing. And here we have different things here. Look at this. It's occupable. Do we have people living in that space? It's an office space. So yeah, we have to click this here. If it were a mechanical room or a storage room in which we don't have people living there, yeah, we can have people entering once a month to see for maintenance. But if people are not there, we can consider this as like that. Okay, so by doing this, and then this condition type, it shouldn't be, it should be unconditioned. Okay, so imagine that that space is not office 1. This is a mechanical room. If this is a mechanical room, we don't have this, and it's not conditioned, so we don't have heating and cooling loads. What happens when we analyze the heating and cooling loads? It's a space, so apparently nothing happens here. If we go to details, we have changed this to the mechanical room, and you see this is not a warning. It means that it's not, it doesn't have heating and cooling system. So here we have a mechanical room. Okay, so the rest of the spaces are green, so that's why we have heating systems. But in the mechanical room, we don't have any heating system. We calculate, and here, when we are analyzing the spaces, we don't have the mechanical room, because in that mechanical room we don't have any, we don't have anything. but it's not outside. Okay, so Revit calculates that mechanical room, taking into account that this is not outside. If there weren't any space there, okay, so now this is the mechanical room. If we delete that space, Revit considers that this is outside, and then there will be a lot of heat losses through here and there. Now Revit considers that this is an indoor space. It doesn't have a heating system because here we have the boiler and the chiller or the whatever. But this is not outside. Okay, so that's the difference. So if we want to have a false ceiling, that it's not it's unconditioned, we have to create another space in the false ceiling and then let Revit know that this is a space that doesn't have a heating system. Or if we are creating an attic without heating or cooling, we can do that. And then, but we have to create a space, because if we don't create a space, then Revit considers that this is outside. And if we don't have here heating and cooling loads, Revit just don't consider this when it's calculating the energy balance of the building. Because yeah, we don't have a heating system there, so we are not losing heat through that mechanical room. Okay, it would be great that if we select or we create mechanical rooms, we can find that the color has changed here, but it doesn't happen in Revit. Okay, for next version, I'm sure they will improve something, or maybe they won't, but anyway. Okay, so that's interesting, and thank you for letting me know, because I couldn't imagine that if you have a false ceiling, Revit considers that this space within the false ceiling and the floor and the roof, sorry, it's outdoor. It doesn't make any sense, but this is what Revit does. Okay, so this is about heating loads in Revit. Now we are going to analyze details in THERM. Okay, I will post another classwork that will be due on Monday, next Monday, and you have to copy the Revit detail here and the THERM detail there. We have to do this with the parapet. We did it on Monday, and today we're going to work with this detail to create something like this. Okay, this is not the detail we are working with, because this is a timber frame construction. We don't have the concrete masonry unit. We will try different details, so probably next week we will work with this timber frame construction, and we will create a model in Revit like this, and then we will try to create the same model in THERM to analyze thermal breaches and all that stuff. Let's work with this, and I didn't save what we did last time, so I'm going to do it again, but I think faster. Okay. Well, if you remember, we created that space, or that level, so that we have the footing level. So we have to bring this footing all the way down up to level 5, which is -4. -4. Yes. This level 4 would be this level 1. Much. -1. Level 0. And let's increase the scale to 4 feet. Okay. Well, this is, I'm going to change this again to something reasonable. It was a foot and 1 inch. Okay. And now, well, I'm going to do it again so that you see what we're doing, but I'm not going to explain every step that we have to create parts in the roof and we have to create parts in the wall. Okay. And I'm not going to do what I did last time. I'm not going to create another wall for the parapet. I'm just going to do it faster and easier. Okay, so I can select all these elements. I can activate the shape handles. And now I have to drag them this way, and let's say this way. For this one, yes, I want to activate all these handles. And I'm going up, parapet. Then this is the thermal insulation. I'm going up, and this is the brick. Where's the brick? Here. And let's go up. I move this up to here, so I wrap. Okay, so this is the concrete block. This is the thermal insulation, and this is the EPDM layer. And if I work with colors to make it easier, I override graphics in view. I don't want any surface pattern. I don't want any cut patterns. I just want the background color. My favorite color, 250, 250, and 100. This is thermal insulation. That thermal insulation, I think it's a different material. It's cellulose. Okay, so that was the rigid insulation, and that was cellulose. So I'm going to use a different color. Not visible, cut pattern, foreground, not visible. And here I'm going to use another solid fill, 240, 240, and 150. Okay, so it's yellowish, but there are two different kinds of thermal insulation material. This is the concrete block. Override. Well, I'm going to select this because this is concrete as well, and even the floor. Well, this is generic. No, we have to work with the floor. So this is hiding view, right graphics, surface patterns. No, cut. Let's keep this, and I want to select gray. There you go. We have different hatches because this is the concrete masonry unit. This is a concrete slab. So this is cast in place. This is a masonry unit. And finally, let's do the same thing with the solid and with the brick, kind of. Okay, we're not doing all this stuff, but we know that we should wrap all these with thermal insulation, and we did this in THERM last time, okay? But just to make sure that we have different materials here, we have thermal insulation inside and outside. This is concrete inside and outside, and this is the brick finish outside, and we have an air layer here, air cavity there. And now we have to do the same there on the roof. So first, I think we need to work with this floor. This floor is just the generic one. One of the problems that Revit has is that it doesn't calculate heating loads or cooling loads through the floor. Is it relevant? Well, it's relevant if we make sure if we don't have insulation in the floor, we will be making a mistake. If we have thermal insulation, a good amount of thermal insulation, probably the heating loads or the heat losses that we have through the floor is not relevant. So let's do it. I understand Revit philosophy. Well, I don't understand Revit philosophy because they are filthy rich and they could have a guy or a couple of guys programming or doing this, but they don't. But I understand the philosophy because if we have thermal insulation here, heat losses through floors are not important. But we need thermal insulation, so we need to edit type. We are going to we're going to duplicate. And let's say this is Fernando floor 1, because we're going to work with 2 different floors. Okay. Oh, I didn't change it. I changed the name. Yeah, but it didn't change. Okay, so in structure, we always have a concrete cast in place. Concrete cast in place. The thickness, it can be 1 foot for floor slab. I think 8 inches would be enough. And then we want thermal insulation. So the first decision we have to make is, do we want thermal insulation above the concrete slab or underneath the concrete slab? Let's try both. We are going to insert something. We want to move it up because this is not a structural element. This is a finish. This is timber. So this is the flooring. No, we don't have timber. Oak. Yeah, we have oak flooring. And this is 1 inch. Quite expensive. Okay, money is not important here. So we have 1 inch, 8 inches, and then I will place thermal insulation below this. So I insert, I move it down. That would be thermal. If this is in contact with soil, I would use here rigid insulation. I wouldn't use cellulose at all. So just use rigid insulation. And thickness. According to Passive House standards, we should have more than 30, if you remember, for floors. I think if we have 6 inches of thermal insulation, that will make 37. Okay, great, that's fine. So we apply, and there you go. So this is the floor. We have the flooring, then the slab, and finally the thermal insulation material. And here we will have either soil aggregates. That will be soil, okay, because this rigid insulation is resting on the soil. We don't have a crawl space. That's the other option that I want to explore, but not now. Okay, so today we imagine that this is soil. Now we have to work with this. So if a footing is at this level, okay, so we have to go down with the wall up to the footing level here. And then I have to work with these layers so that so first is to create parts, then to show these handles. And now this is the flooring. I can go this way. This is the concrete slab. I would go up to this point, and this is the thermal insulation, and I will go up to this point. This element will rest on the slab, and the concrete masonry units will go all the way down to level 5. Okay, and now we have to stop this. And well, this is what we're going to study today, first with Revit and then with THERM. We can move this down because here we have a thermal bridge. Okay, so I'm going to make this yellow. This is 250 and 100. Apply. This would be gray. And the background, material, color, grayish. Okay, so all the gray layers are concrete layers. And yeah, I can move this down up to this level and this up to this level. So here we don't have the thermal bridge, or we have a thermal bridge, but at least it's not as bad as doing this. Okay, so this is worse because we have all this front without any thermal insulation. At least if we move this down, and that's better. And finally, we would need a footing here. So how can we create a footing? Well, we can do that in 3D, but if we are just working with that detail, we're working with annotate region, field region, rectangle, and that is the footing. And now we override by element. Surface patterns, I want concrete, and the background, I want a solid gray background. Okay. The I mean the bearing wall. This is the concrete masonry unit. We need a footing. That will be soil. Okay, so I'm going to create another region with this because I'm going to place soil all the way here. There you go, finish. And now this material by element, I will make the background, well, the foreground by material. I want this to be soil. We have earth. Apply, okay. So that's nice because we have earth here, the footing, the, well, if we should have aggregates here, but okay, that's fine. We have the rigid insulation on the soil, and then there's a concrete slab here, and this is the flooring. This one, this is the flooring. This is the gypsum wall, cellulose, concrete masonry unit, rigid insulation, air cavity, and what do you call it? Brick. What? Brick. Okay. How will it work? Well, we don't know. Let's find out. And now we have to open THERM. Okay, but we look at this, and well, we have to wrap this. I'm going to do it. So I'm going to create another masking field region, and then I'm going to wrap this element here, and that will be yellow. Two 50, 250, 100. And then I would need the waterproof layer, but we are analyzing the thermal behavior of this detail. So when it comes to thermal behavior, these waterproof layers are not important. They have a, so we can use them to prevent condensation and infiltration. But if we are just analyzing the heat losses, these layers are not important. So we're analyzing heat losses so far. Okay, so now we have this section, and it's in, I don't know, 15 minutes, we can fix this, and now it's looking like something professional. Okay, if we don't have layers, or you can well, I'm using colors. I don't know, because I feel like using colors now. But if you create, if you do these kind of things by using hatches, I think it will work. So one of my favorite architects, which is Álvaro Ziza, a guy from Portugal. Okay, he's getting old. Álvaro Ziza, detalhes construtivos. So I'm using my Portuguese. Okay, so do we have details? Yeah. Okay, so he's doing this kind of details, nice details. We're not going to analyze this, but he's using hatches in black and white. And as long as you have a legend, that's perfectly fine. Okay, so you don't have to use colors. But if you create construction details just like this using elegant hatches, that's perfect. Okay, so I don't have anything against using black and white and gray. So it's more elegant. Using colors, you have to be careful, because if the color combination is not good, it won't look like a professional detail. If you use always black and white, it looks more professional, because I think I've told you many times, when you are working with projects, you have to print out these sheets of paper, and then you have to copy. And nobody uses a color plotter for this kind of drawings. So everybody prints and everybody copies in black and white. Okay, so if you understand the drawing with black and white, that's good, because you will understand the drawing if you add colors. Okay, but if you add a lot of colors and then you print it black and white and you don't understand anything, that's a problem. Anyway, where did I learn how to do this? Well, there was when I was young, when I was younger, there was a very nice journal. I think I've talked about this journal, Tectonica. Okay, so that was the kind of details. Okay, when I was a student, we were, I don't know, we wanted to work in this journal. Okay, so we wanted to be good enough at drawing to and we sent our CV to this journal because we wanted to work. We were mad, desperate to work with these guys doing this kind of details. And now I think the journal doesn't exist anymore, the crisis. But everything I know about construction, I think I have learned by looking at these pictures. Okay, so I'm using these colors because grayish and yellowish for the thermal insulation. Because I don't know, when I was a student, I tried to imitate, I tried to copy this elegant. Okay, so it was like something outstanding, being able to do something like this. They didn't use Revit at all. It was AutoCAD or any other software in the 90s. But here we are using hatches. This can be Revit. It's good enough, it's elegant. And as long as we have a legend here with 1, 2, 3, that's fine. Okay, so you have to find your own. Actually, I like when in doubt, do not use colors. Okay, so it's more elegant if you use these kind of details. But you have to find your own way to show what you want to do. Okay, so it doesn't mean that you have to do this, that you have to use for the yellow the 250, 250, 100. No, this is the color that I use. That you can use any other one, or you can use with hatches, and that's perfectly fine. Uh, Now I think we shouldn't use less colors. Anyway, we're, let's move on. So we have this, but by looking at this, it's not completely defined. So there are a lot of things that we can do with call outs. I'm showing you how to create call outs and improving this detail in advanced representation. But at this point, I think that's fine because by looking at this, we know a lot of information. And we know that we have different materials. We understand what the structural materials are. The grayish, it's always the structure, the thermal insulation, and then this one is the finish. So there's a lot of information here. And here, yeah, we have fixed, we know the order. Okay, so we know that first we have the footing, then we start building this, then we place the slab. Well, first we place the rigid insulation on the floor, and then we place the slab over the rigid insulation. Then we start with the cellulose here. We know that we need something to hold this weight there. Okay, so there's a lot of information here. But we are going to work with THERM. So let's open THERM. Okay, updates, cancel. And I uploaded a THERM template on Canvas. Okay, this one. So anytime you start a new drawing, you should upload this one because there's a lot of information here, as I told you before. We have to draw view, sorry, the grid. We have to open that template. And when we open the template, we have to activate the grid as well. We can delete all these polygons. Yes. And I told you that in the zoom, we should work with 20. And we have to start right here in the middle of the screen. Okay, so don't start close to this because we cannot extend the screen. So we have to move down. So we have to start here. What is the in options, preferences, snap settings? We have 0.5 inches. Let's make it 1. 0.5, it would be more accurate, but we are doing something, we are not including a lot of details, so 1, I think it will be easier. And 20, I'm going to use 15. Okay. And now we have to trace, or we have to start doing what we are doing here. If we look at the materials, where's Revit? Here. If we look at the materials, all this gray thing is the same material. Okay, so we have the wall, the footing, and the slab. It is the same material. Usually, if we do something like that, we have less trouble working with THERM. Okay, so instead of working with rectangles, I'm going to use polygons now. So I'm going to start from, so this is the top of the detail. So I'm going down and I go all the way down up to the footing. I'm working with the wall. Yep. I'm working with the wall and here, okay, there. And now I'm creating the footing. Dimensions are not important. So this is 1, 2, 3, 4, 5, 6 inches. Well, I'm going to make it a little thicker. Then I go this way here. And what's the thickness of this wall? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, I think the concrete masonry unit wall is 10 inches. And then I go all the way left, and this is the concrete slab. It was 8 inches. 1, 2, 3, 4, 5, 6, 7, 8. And then I go this way, and this way, and this way. Okay, so to me, I'm going to zoom out. Okay, to me, this is concrete. So we can use concrete here. Okay, so everything is concrete here. Then we have to start doing something different. I'm working with here we have a rigid insulation. So now I can use a rectangle and I can create 1, 2, 3, 4, 5, 6 inches of rigid insulation here. I select this, and this is extruded polystyrene. So this is a rigid insulation. Then I have, I remember that we had cellulose here. I don't know, let's say 1, 2, 3, 4, 6 inches of cellulose. So I can select this and use cellulose, either this one or that one. Okay. Then I had the rectangle. And here we had, I don't know, 4 inches of rigid insulation again. We had the air cavity. We're not going to work with the air cavity because air cavities, we have to learn how to work with these air cavities. And we're going to add a 4-inch brick layer, 1, 2, 3, 4. Okay, and let's make it brick. Do we have brick? Aluminum, foam. We don't have brick. Come on. Mineral, hardwood. Well, cellulose, aluminum. We don't have brick. Okay, so let's make it concrete. It's not, when it comes to thermal performance, brick, concrete, it doesn't make a difference. But I thought I had already uploaded the Greek material here. Well, I don't find it. Okay, so this is the detail. And finally, we have the soil. So I'm going to work with a polygon, and I'm going to create and this should be soil, earth, or something like that. We have soil. Okay. Well, we can move this up. I don't know, but it's pretty similar to this. Okay, so we have the rigid insulation, the concrete slab. We didn't add the flooring. We can do it. So here I can have an inch of some kind of wood. Redwood. Okay, redwood, cedar, hemlock, two-glass. Doesn't matter. It was oak. I don't know if we have oak here. Hardwood, oak. Okay, we do. And what else? Oh, we have the gypsum board. So we can create an inch of gypsum board here. Gypsum board. Okay. Now we have to start working with the boundary conditions. Remember that if we don't have any heat interchange, we have this, we have to select boundary conditions, draw boundary conditions. We select this, and this is adiabatic. Okay, so if the detail continues in this direction, this should be adiabatic, this should be adiabatic, and this line should be adiabatic because the detail continues left, right, and up, and even down. Okay, so that should be adiabatic because we have soil going down. But the rest, okay, so we start with something easy. This is a wall. So this is a wall int, because this is inside. Okay, this is a floor inside, and now I found out that I didn't upload. I have walls and roofs, but they don't have floors. Okay, I'll do it. I'll fix it. So let's use a wall int. It's not going to be extremely accurate, but it will be good enough. And now this is inside. So we have to select this, and we have to go to libraries, set boundary condition. And remember that here we have wall int, but here we have to type interior. And here we have to set boundary condition. This is interior as well. And now we have to set these boundaries. This is clearly a wall X. What is this? Well, I'm going to make all these wall X. And this, what is this? Is either, well, in theory, the heat will go this way and then it will go up. So here at this point, the heat will go up. So this is better. This is not a floor. It should be a roof. X. Roof floor, we need to know that if the heat goes up, it's a roof, and if the heat goes down, it's a floor. Okay, so through this point, the heat goes down, but then the heat will go up in this direction. So this can be a roof. And now we have to select all these boundaries. We have to set boundary condition, and we have to make it exterior. Okay. So now, if you know some prayer, just do it. Let's pray. And if you don't, I don't know, just because we need luck to do this. So let's calculate. Oh, it's working. Yes. Okay, so it's working here. You see that this is the temperature profile. So when the temperature lines are parallel, that means that, well, we can do this with the Excel file. Okay, so this Excel file only works when these lines are parallel. So as of this point, all these lines will be parallel, and then we can calculate what's going on in this wall with the Excel file. But when lines are not parallel, so as of this point, lines will be parallel again. But in this corner, this is the temperature profile. Outside we have 0, inside we have 70. Can we find out this? Yes, if we, well, before doing this, I'm going to display options. First, the flux vectors. Okay. So yeah, is it a thermal bridge? Well, it's a weak point. Okay, so if we don't wrap the structure with thermal insulation, we can have this. Okay, so you see that the arrows, the vectors are very small here. So that means that there is no heat flow in this direction. And when the vectors are bigger or longer, it means that the heat flow is increased in this. And it makes sense. So this is, yeah, because we have the thermal insulation here and we don't have a continuous thermal insulation. Okay, so that's the first option. By the way, if you are doing this, you can printing things in THERM is quite complicated. So I recommend you print screen. And if you want to print the screen and create a PowerPoint, it would be much better. Okay. And then we can always compare the THERM results to the Revit detail. Okay, this is Revit, this is THERM. Well, I try to make dimensions the same. Okay, so I didn't look at the Revit file when I was doing this, but just try to adjust the dimensions so that they are looking alike. But with THERM, we can have this with the flow, but we have a lot of information here. So if we go to display options, if we have to show legend. Okay, so when we are having this color flux magnitude, we show the color legend and the polygon.
Choked out by the bag, and then his
Sorry?
boy with the sniper from like 12 blocks over was like, "Woo!" Headshot one of the dudes, and then fucking Keanu just takes on the other guy in this like 5 to 7 minute fight.
At the beginning, have you ever seen that movie Through? Yeah. No? At the beginning of that movie, he takes on like straight up like a dozen guys come to his house.
Yeah, no, I've seen. Yeah,
and he like fucks them all up, and he like.
Yeah, it was quite an interesting conversation. But if you don't mind, I'm muting you. Okay, so we have to show polygon outlines. We click OK. Okay. So now we have the legend. And well, we see in colors, and it's not just the color is nice, but we have to find out the heat losses that we are having. Okay, so we have this color legend, And I think this is useful. We can take a screenshot here. And I don't know, we can have different Revit screenshots. Like this. And we do have information. We have written information in this calculation. We can see show you, or we can show you factors. Okay, so that's interesting. What does it mean? We know the U factor or the R value. Okay. So the R value is 16 here and 4 from the interior. Why does it happen? We are used to having an R value when we have two parallel faces. Well, parallel faces when we don't have any corners. Okay, so if we are looking at this detail, we have this face and that face, and then we have an R value. But when we have corners and angles in 2 dimensions, the heat tries to go well. This is a typical in THERM. It looks like it's going to finish, but it doesn't, and then starts again. And eventually it breaks. Okay, so this is THERM. Okay, so we have this. We had a different, by the way, if you haven't saved what you have done, yeah, you can forget about it. I'm going to okay, I want to take this. There you go. Okay, this is what I want to explain. We have the R value, and well, this is 16. Why is it 16? I'm sure that if we have the R value of that detail with this thickness of thermal insulation here, that thickness of thermal insulation there, so it will be close to 50. Okay, why is it 16 and why is it 4 here? Because this is the average R value. Looking at this, yeah, so in this line, we have thermal insulation, concrete, another layer of thermal insulation. So that would be a high R value. If we go this way, this should be close to 30. But if we go this way, we don't have any thermal insulation. From this point to that point, we don't have any thermal insulation. So there are a lot of lines. So this is calculating the R value through this line, through that line, and then through thousands of lines in different directions like this. So there are a lot of lines in which we don't have any thermal insulation. So if we don't have any thermal insulation, the R value it's close to 1, 2, so it's very low. So if we have the average is 16. Okay, that's interesting because we can have a very high R value, above 50 for walls, above 80 for roofs. But if this detail is not solved, we are having a lot of heat losses here. How much? As much as this, with this R value, then we have to calculate the U value, and then we have to take that into account. Revit doesn't have this. So Revit doesn't calculate the heat loss through the thermal bridge. So that's why we need THERM. Okay. First, by looking at it, we know where the problem is. So probably we can make a better detail than this one. And then we can quantify the heat losses with this R value. But the explanation of this is that we have 16 and we have 4. And that's another explanation here. It takes into account the surface. Okay, what is exterior here? Exterior is all this surface, all this line. But interior is only this corner here. So we have much more exterior envelope than interior. But the heat flow is the same. So we have a heat flow here, and it's going either this way, that way, that way, that way. So that way, if we compare the heat that we are losing with this surface or with this envelope, we are losing a lot of heat. But then if we compare the heat that goes through all that envelope, yeah, the proportion is lower. So that's the explanation. This is difficult to explain, so we will go over it later, because eventually we will have to quantify heat losses through the roof, walls, and doors, and this is what Revit does. And then we have to quantify heat losses through the thermal bridge. So I'm not happy with this detail, because yeah, I knew that we are going to have a thermal bridge here. Okay, so I'm not what I'm doing, yes. Okay, I think it stopped. And now make sure that you save as, and this is floor 1. Okay, so make sure that from time to time you save the THERM file, because it's pretty unstable. Okay, so instead of doing this again, I'm going to start another detail. So I'm going to close THERM. I'm going to open THERM again. I'm going to open the same template. I'm not opening the floor 1. I'm opening the template again. Because if you delete and then you do it again and you delete again, the THERM file gets corrupted, and then you have to start again. So I'm going to start again, but I think now I'll do this faster. The grid, zoom, okay, 16 is fine. And I'm going to work with the with this. Oh, no, sorry. Delete polygon. Because in options, references, I want to start with 1 inch. 1, set. And now the zoom, I want to make it 10. There you go. And the polygon. So I was doing this. I think try to remember the same thickness. I think it was 6 inches. 1, 2, 3, 4, 5, 6, or 8. I think it was 8. I don't remember. Now we go down. And now it was 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we'll go up. That was concrete. Then there was cellulose here. And now I'm going to change the detail, and I'm going to include the thermal insulation above, over the slab instead of below or under the slab. So this is the extruded polystyrene, okay? And I can go, so I'm going to do it better now. So I'm going to include this. And then I want to create 4 inches of concrete here. Concrete. And finally, I will create the soil. Okay, and that will be earth or soil. Okay, I'm not doing the flooring because it's not relevant. And now I'm going to work with the boundary conditions. I'm going to select this one. This is wall interior. And if I set the boundary condition, it has to be interior. And now I'm going to select all this. Let's make it wall exterior, libraries, set boundary, exterior. The rest is adiabatic. Yep. And now we can calculate. Okay. And if we look at the colors now, the color flux magnitude, show polygon lines, and show legend. Okay, let's compare these two details. The colors are not relevant. The relevant information is the numbers here. Okay, so you see that the numbers in this legend go from 0 to 13.5. And here the numbers go from 0 to 4.7. Okay, so although the color is the same, you could say, okay, we have more heat losses here because we have more red and green color. No, because here the values, so the value of this green or red color is much higher than here. Okay, so the colors are the same. Here we have more red and green colors, but the value of a green color here is 2 point something, and the value of this green color is 8.5. Okay, so yeah, we have this detail is better than this. We have the same materials. We only have changed the order. Here we have the thermal insulation underneath the slab, and here we have the thermal insulation above the slab. Here we don't have a thermal breach. No, here we don't have a thermal breach. Here we do have a thermal breach. But the best way to understand this is just by comparing this, and this. Okay, because here, that's the explanation. Here we have this heat flow. We don't have a continuous thermal insulation. So I have to take a screenshot if it's possible.
Hey, Fernando.
Yep.
So are the colors in THERM with that temperature diagram, do those remain the same? Is it sort of like an infrared camera where the colors stay the same, it's just the scale changes?
Exactly the same. The color stays the same. The scale changes. So
Gotcha.
that's the explanation. There's a, I mean, somewhere here there is a way to change the color scale. Yeah, we can do that. But if we have the color legend and we have the values here, I think it's enough. Okay. That yeah, we can work only with these colors, but then we have to change the scale. Yeah, just the same as in infrared cameras. In fact, this is what the infrared camera is doing. Okay, so the infrared camera is giving us information about temperatures, not about anything else, about temperatures. So we assign a temperature, and the temperature or the heat flow through this wall depends on the temperature. So it's just by looking at temperatures as well.
Gotcha.
But I think if we compare this and this, and then we compare, I want to show the constant flux lines. No, not this one. Display flux vectors, sorry. Okay. And window 10, 8. There you go. Okay, so by looking at this, we look at this detail, and we see that there's a thermal bridge here, and we have the color legend so that we can understand this. And here we can even show the R value. Okay, so here we have the color legend from 0 to 4.7. Here we have the color legend from 0 to 13.5. And if we show the U factors, the R value, okay, so this R value is 31 and 11, the exterior and interior. So let's make a screenshot of this. It's too big. Okay, that's enough. Okay, so now by doing this, we compare both solutions with and without the thermal bridge. With a thermal bridge, well, it's not a thermal bridge because we have this, we have this, we have this, so it can be even worse. Okay, so it's not a bad solution. I mean, this is not a bad solution, but this is better. That's the, and we can quantify how much better this is. So this is the R value, it's 31, and the R value here, it's 16. The maximum heat flux is 4.7 here. The maximum is 13.5 there. Okay, so we can quantify with numbers, and we can say if this is 4.7 and this is 13.5, we lose 3 times as much heat through this detail than through this one. Or if we want to show the thermal resistance, this is 16 and this is 31. Okay, so we have twice as much thermal resistance with this detail than with this one. So we are quantifying, we are not saying, oh, this is better. Yes, but how much? Imagine that you are working in a retrofitting a house or a building, and you have to make that decision. Making that decision from at the initial stage of the design process, it's a piece of cake, because I can decide, okay, do I want the thermal insulation here or there? But when you have the building and then you have to change, or you have to replace this thermal insulation by this one, you have to remove the flooring, you have to, so it takes a lot of effort and money. So is it worth it? Well, we don't know how much energy I'm going to save if I do this. Well, you're going to save this, and this is, I don't know, $30 per week, $30 a week, $120 per month. How much does it cost? $2,000, $2,000. I need a couple of years to, so your client has criteria to find out if it's worth it or not. It's not just, no, trust me, I'll do it. Yeah, okay, I trust you, but how much will I save? Can you give me some data? Yes, I can give you simulations. Look at this. This is, yeah, so this is much better than this one. How much? Double, because this the R value here is 31, and the R value there is 16. Yeah, so double. Okay, double. Sounds good. So let's do it. Okay, so I know there's a lot of information in this lesson. First, you have to do this in Revit. In Revit, you can have a feeling of how things are going, and this is the number. Okay, this is 65,000 in summer, 19,000 in winter. Okay, that's fine. You can increase the thermal insulation in Revit. You can improve the quality of windows, and then you can find out how much you're improving the thermal performance. Okay, but in Revit, you cannot go to the detail. To go to the detail, in Revit, Revit doesn't understand about thermal breaches. But if we want to understand how a thermal breach impacts, then we have to go to THERM.